Stanford Professionals in Energy presents our keynote speaker, Dr. Sally M. Benson. You may clap.
Hold on, I get to say a few more things. Dr. Benson is the co-director of the Precourt Institute for Energy. She is the director of the Global Climate and Energy Project. She's affiliated with the Stanford Woods Institute, the Stanford Center for Carbon Storage. She is the co-author of over 160 technical publications. Her research interests include geological storage of CO2 in deep underground formations, technologies and energy systems for a low-carbon future, and geotechnical instrumentation for subsurface characterization and monitoring. And one last thing. I happen to know that Sally has a new puppy. And I have a small gift for her, and can anyone guess? A duck, of course! Welcome, Sally Benson.
Okay, I'm guessing that I'm guessing I have to turn it on myself. All right. Anyway, what a fantastic group. What a pleasure to be here. It's so interesting. I could have spent, well, I'm lucky I get to spend the whole rest of the evening with you. So the organizers of this event figured I couldn't cope with this 15-second business, so they gave me a pass. So this is a regular talk. So we're going to change. I'm in control of when we change the slides. So anyway, so what I'm going to talk about is sort of a big picture on the future of energy, and then I'll wrap up with a sort of a new dimension of a climate solution that is beginning to get some traction and is likely to be necessary in the future. And that's putting carbon dioxide back underground. Okay, you have 15 seconds. I want you to look at this picture. What do all these pictures have in common?
Talks about today.
Movement. Oil products.
Transportation.
Hey, who got that? Energy, yes. That's right. Okay, we use a lot of energy. So the average person in the United States uses 250 kilowatt hours per day per person. A lot of that is embodied in stuff, all the clothes we wear, the newspapers we read, automobiles, heating and cooling, planes, food, transporting stuff, gadgets, and so forth. Okay, but that's a very abstract number, 250 kilowatt hours per day per person. How much is that? Okay, if that were coal, like if we had to put the coal in our basement and store it, basically we'd need 2 African elephants worth per year of coal in order just to meet our own energy needs. Okay, well you say, I'm not going to use coal. Okay, petroleum. How much would we need? In our basement, we need to have 60 barrels of oil in order to meet our energy need. Okay, that's extraordinarily big. So where do we get that energy from? Coal, oil. Oil is the single biggest source of energy. Natural gas, nuclear, renewables, and so forth. Over 80% of the global energy supply comes from fossil fuels. Okay, so what's the issue with that? Well, basically we have carbon and hydrogen. These are hydrocarbons. We combust that with oxygen and we make carbon dioxide and water and some other stuff too, but that's basically what we do. So this is basically global warming pollution. So if we look at carbon dioxide emissions, this is a chart showing from 1990 to 2015, and you can see significant and steady growth throughout this entire time period. And today we're up at nearly 37 billion tons of carbon dioxide are emitted into the atmosphere. Well, what's wrong with that? Well, it causes global warming, as I mentioned, and I want to focus in on 2 impacts that are local, things that matter to us here. So the first one is sea level rise. So moderate estimations of the amount of sea level rise are on the order of, say, 4 feet or so, right? It could be much more than that. But this chart shows that 4 feet, which is the minimum amount we expect by 2100. And you can see all this part of the South Bay is now underwater, okay, even with 4 feet of sea level rise. So this is a real impact that is going to affect us. So this is another thing. This is about the snowpack in the Sierra. And there are 2 scenarios here. One is what we would be, like if we have an average of 2 degrees sea warming in the world, this is how our snowpack would be changed. So everything that's red, that's a decline. Okay, we can see about the majority of the Sierra, about 70% to 100% decline in the snowpack. Okay, what's the problem with that? We actually rely on the snowpack to store half of our water. We have big reservoirs, but we rely on that snowpack to hold it off until later in the summer, where then it goes into the reservoirs and then we can use it. So very significant impacts. If we don't control this better, if we have significantly more warming, basically we lose the Sierra snowpack entirely. So real impacts that can affect our lives. And if we think about here in San Francisco, we drink beautiful water that comes from the Sierra. So exactly this kind of water. Okay, so what are we going to do? Emissions need to go down. Okay, I think that's broadly accepted. And there's been recently a new assessment done by the Intergovernmental Panel on Climate Change. And they looked at a specific scenario that said, well, what if we could actually limit warming to 1.5 degrees C, not 2 degrees C? So a little bit tougher of a target. And this is just a conceptual, actually it's a quantitative graph, but it illustrates sort of key concepts. So here we are with emissions about 40 billion tons a year. So if we're going to stabilize at 1.5 degrees C warming within less than a decade, we need to begin to precipitously drop our emissions. But very interestingly, what we see is a couple things. One is there going to be some difficult to eliminate emissions. Those are things like airplane travel, long distance transport of goods over the seas, for example, steel manufacturing, cement manufacturing. So in order to compensate for that, we're actually going to have negative emissions. In other words, we're going to have to start taking carbon dioxide out of the atmosphere and sequestering it someplace where it can't get back into the atmosphere. So all of this reflects this current understanding that we're going to need to actually be pulling carbon dioxide out of the atmosphere. But very importantly, we've got to deal with this decline in emissions to get things moving. Okay, so I'm going to show you a chart. This is sort of my roadmap of what we can do between now and say 2100. But of course we have to do it right now as well. So the first thing we're going to talk about is that one can forecast that we're likely to need twice as much energy to meet global demand. We're going to have 11 billion people. If everybody lives with the carbon intensity or the energy intensity of someone in Italy, which is about a quarter of what we are, we'll need 2 times more energy in the world. And if we had exactly the same energy system, we'd have twice as much emissions. Okay, so that's going to be our baseline. And we're going to look at 2 things. One, if we improve carbon intensity, meaning we decarbonize. And 2, if we can improve energy efficiency, how can we cut away at this to first get this rapid reduction in emissions and then get to this negative emissions? Okay, first thing, conserve more energy. Behave differently, essentially. Second thing, we can improve the technology that we use. We can drive more efficient cars. We can have more efficient refrigerators. We can have better designed buildings. Next, in the short term, we can switch from coal to natural gas. Coal is the most polluting of all fossil fuels. If we can switch to natural gas, we can reduce our emissions by half, and all of the other kinds of pollution associated with coal can be eliminated. And then we can switch, the big switch to renewable energy. So, wind, solar, geothermal, bioenergy. And of course, we're going to need battery storage and other forms of energy storage. We can then switch to electric vehicles, okay? And those both have less carbon emissions and can be more efficient. We can then use something called carbon capture and sequestration. And this is something that is not so familiar to many people, which is where we're going to go, sort of a deep dive on that. We can use nuclear power. I know there's a very divergent set of views about this, but it certainly is a decarbonized source of electricity that can be operated at scale. It's here today. And then underneath this, we need to completely reinvent how we think about the electric grid. We're going to need to modernize that infrastructure with new communications and controls and so forth. And we're going to need to be able to accommodate a huge amount of electric vehicle charging, which is going to both be an opportunity for using electricity for other uses, but also create stresses within the electricity system. So in the rest of the talks you're going to hear really wonderful examples of many of these things. We're also going to need new technology. That's why it's so important that we continue to invest in innovation. You know, we'd like to be able to make hydrogen. We'd like to be able to make fuels. If we just take carbon dioxide, water, and renewable energy, we'd like to be able to make a fuel, okay? Have a neutral cycle. And then finally, at some point, we're going to need to use carbon dioxide removal. And we all have to do this all really quickly, and we need to do all these simultaneously. So now I'm going to dive into this last topic, try to introduce you really briefly to the topic of carbon capture and storage. And basically the idea is that if you have a cement plant or a steel plant or any kind of emission source, particularly those difficult to eliminate emission sources, we can capture that carbon dioxide. So what comes out of a smokestack is about 85% nitrogen, and the rest would be carbon dioxide. If it's a gas plant, it will be less than that. So we have the smokestack with carbon dioxide and another gas. We need to separate those. We can then compress it. It makes it a liquid. We put it in a pipe, and then we can sequester it. Okay? And when we talk about sequestration, what we're talking about is putting it back deep underground, essentially where the carbon dioxide came from in the first place. So is this a wild pie in the sky crazy idea? Well, maybe yes, but the reality is it's being done today. This is a project in Canada. This was a coal plant that they had. The Canadians decided they wanted to continue to use coal in Saskatchewan, but they said we don't want those emissions, so they built a big capture unit. This is 110 megawatts. So this was the first one. The second one is now operating in Houston area, 140 megawatts. So this is happening today. It's not to say it's not it's expensive to do, but nevertheless it can be done and is being done. So how do you do this? How do you capture the CO2? Here's actually a plant. This is one in China. This is a very small plant capturing just 3,000 tons per year. But basically the idea is you have the flue gas coming through a tower. You contact it with a liquid that absorbs the carbon dioxide. Then you take that carbon dioxide and you put it in a second tower, the regeneration tower. You put in a little bit of steam. The carbon dioxide is released, and then you use that solvent over and over again. So this is how it works. Okay, now where are we going to put it? Well, I said we're going to put it deep underground. This is a picture. This is actually very close to us. If we were to drive from here where we are today over to the foothills of the Sierra Nevada, we would be driving on this huge, you can think of it, a bathtub or a basin full of sedimentary rocks, meaning sand and clays and so forth. And what's interesting about these formations is that you have an alternating layer cake of sand layer, clay layer, sand layer, clay layer. And you can actually put the carbon dioxide in these sand layers, and the clay layer will keep it trapped. And the reason that we know this works is that this is exactly how natural gas is trapped underground, or this is exactly how oil is trapped underground. So where can we do this? Is this a very niche opportunity, or is it widespread? So every place on this map where it's dark, it's likely we can do this. The areas that it's sort of medium gray, well, we might be able to, we don't know yet, we'd have to look. So widespread. The capacity for doing this is enormous. We could easily do this for hundreds of years and still have enough capacity. The issue is more, do you have it located where you want it or where you need it? Okay, so this used to be an animation. Anyway, so the way this works is that you inject carbon dioxide at the bottom of the sand formation. It wants to rise because it's more buoyant, so it's lower density than the water. It rises and then it finds the clay layer and this traps it underground. Okay, and then again, this is exactly how natural gas reservoirs are formed. You do this about a mile underground or deeper. So we're not talking about doing it shallow. You don't do it in groundwater, and you do it where you have a really good understanding of the rocks. So are we doing this today? We are. So this is a project in the North Sea. This was the first project that was deliberately done to sequester carbon dioxide. Started in 1996. It's in the North Sea, 1 million tons a year. Okay, that's a big number. They used seismic monitoring technology, basically like a sonogram for the Earth. And now they've been doing this. They continue to do this. They put more than 20 million tons underground. And this is a picture. So, and the carbon dioxide they get here is actually produced along with natural gas. They do the separation offshore, and they pump it into this formation. So when they first started doing this, they didn't know if they could keep track of where the CO2 was with seismic imaging. So they started to do this, and lo and behold, they got fantastic results. So this is what's called a seismic image. We look at from 1994, 2001, 2004, 2006. Before the injection, you look at these pictures, nothing too interesting. This is like a map view. This is a cross section. Okay, start injecting CO2. Boom, you can see it right away. So that's, again, you can see CO2 trapped under all these little layers. You see it's not escaping, so it's effectively trapped. And then looking at the map, you can see over time this grows. And basically you can keep track of exactly where the carbon dioxide is. So there's a lot of interest, though, in using CO2 to generate some income. So it turns out that you can actually put CO2 into oil reservoirs, and it will enhance recovery. And so here's a picture of that. The idea, this was actually developed in the 1970s because we were worried we were running out of oil then. And so they thought, well, we can get more. So you put carbon dioxide in, you put some more water, and you push out the oil. And meanwhile, you're just filling all this reservoir up with CO2. And we've actually done work to show that you can basically put back as much carbon in this oil reservoir as you've initially taken out over the whole lifetime. So that's sort of this idea of putting it back. Okay, so of course, these solutions only work if we can do them at gigantic scale, billions of tons a year. Okay, that's really the issue. Can we do this at scale? So what evidence could we have? Well, it turns out in the United States, we already inject 3.2 billion tons of water underground. It's actually easier to inject carbon dioxide underground than water. So this is just a real example of something that we're doing today at the scale that can be an analog to what we're interested in doing. So just to wrap up quickly, where are we today? 18 projects, 31.5 million tons a year of CO2 that's captured that would have otherwise just been emitted to the atmosphere. A lot of action in North America. Norway was really the pioneer in doing this. Now we're seeing in the Middle East, very interesting, the first steel manufacturing is now they're capturing CO2 from that, and a little bit of work in China. So that's where we are. I hope this quick introduction sort of piqued your curiosity about this technology and the important role it might play. Thank you very much.